This is Unit 6, Video 3. In this video we will talk about pressure, the other important variable with gases, a measurable. You can measure pressure with gases. Usually we talk about pressure just like temperature in terms of gases. Now pressure is the force that gas particles exert on objects because of their collisions with those objects. So if you have any object in the air, just in the atmosphere, say if you have a cylinder, that cylinder is being bombarded with gas particles from all directions, and the gas particles are actually exerting a force on that cylinder, and that force is we call pressure. And a vacuum is actually an environment that has no air pressure. So outer space, for example, is considered a vacuum because there is no air pressure in outer space. And there's no air pressure because there are no gas particles there. In truth, there's a really, really small amount of them, but we can consider it being empty, essentially. Now, from physics, we're going to also give you a little equation from physics with pressure, just like with temperature. The pressure is defined as force over area, and over surface area usually. And so, if you have, for example, a big area, and then you have that same cylinder that's sitting on this big area, what happens is the cylinder has a force, and the force is due to gravity. There's a gravitational force that's pushing down. It's technically from the mass, related to the mass of the cylinder. But then if you take a look at the area of its base, you can divide that force by the area to find out the pressure. And that's kind of the idea. Now, where this applies is essentially the atmosphere, which is the air above us, can be thought of as a huge cylinder of air pressing down on every area of the Earth. And we're going to define atmospheric pressure. We're actually going to give it a number. There's a certain amount of pressure that is applied at our level when we're living. And that's essentially how it is defined. Here it says it's about 10,000 kilograms, which is quite a bit, definitely quite a bit. Okay, so this has an effect on elevation. So for example, if you are higher in the elevation, so say if you go up to Denver has thinner air, which means there's less pressure. St. Louis, where we're at, has more air because we're lower and we're closer to the sea level, so we have a smaller pressure, or rather we have a bigger pressure, sorry. The pressure is higher here, higher pressure, and then lower in Denver, which has an effect actually on many properties in Denver. So here it says the higher the elevation, the lower the pressure, since air is thinner. And think of it as the higher you go in elevation, the closer to outer space you get, and outer space has no pressure. So that's why you get lower and lower pressure as you go higher up. Here are the units of pressure, and we're going to show you how these got defined, but there are actually a bunch more units of pressure than there are of temperature. We only talked about 3 for temperature, and here we have at least 6 for pressure. So the standard one that we begin with is ATM, and this is from the word atmosphere, so 1 atmosphere, and this is referring to the atmosphere above the Earth. This is also related to pounds per square inch. Probably the most common use unit for pressure is PSI, kind of like Fahrenheit is the most common use. So 14.7 PSI, kind of a weird number, but 1 atmosphere equals 14.7 PSI. This also equals 101,325 PA. Now PA is a unit used by physicists. So in physics, this actually lines up really nicely with forces and so forth that you're studying. And this is actually called pascals, named after a famous mathematician, physicist, Blaise Pascal of yesteryear. And obviously then you can convert this to kilopascals, just like you could anything else, but usually kilopascals is used. And then we have this strange unit, 760 mmHg, which refers to millimeters of the element mercury, also referred to as torrs or torricelli. And as you'll see, this is also named after a scientist, Torricelli. And then we have bars, what are called bars. The European Union, in Europe they use bars much more than we do here in the US, which is related to Pascal. So a bar is 10 to the 5th or 100,000 pascals, or 100 kilopascals. So you can be asked to convert from any of these pressure units to any other pressure unit. Now, the pressure gauges have different units on them. Usually they have at least two. In this case, you have, it looks like kilopascals and psi for the common folks. So psi down here from 0 up to 15 psi, and then kilopascal from 0 to about 100. And that's kind of the idea here. All right. Now let's show you from the chemistry perspective the most important unit of pressure. One of the most important is actually millimeters of mercury, because pressure got defined using chemistry. Now they defined it using good old mercury, or hydrogyrum, liquid metal. And what they did is, essentially, scientists way back in the day, they experimented with this, and they got we'll say a bowl filled with mercury, and then they took a tube, a very high tube, a meter-long tube essentially, and also filled it with mercury. They inverted it and placed it in the mercury, and the amount of mercury that came out was actually about 1/4. About 1/4 of the mercury came out. About 3/4 of the mercury stayed put. 3/4 stayed, and about 1/4 came out. Now this is interesting because the weight of the mercury here is pretty high. There's a big force pushing down because of the weight of the mercury. They use mercury because mercury is very heavy. It's a very heavy liquid, so the amount of force pushing down is pretty tremendous. But that was able to be balanced by the amount of air pressure coming pushing down on the mercury. So essentially the air particles that are out here from the atmosphere, the column of air from the atmosphere, was actually pushing against this mercury, keeping it up. By the way, if you were to place water in here, water would not have any chance. Water will actually sit in here. It would not even come out. That's how much pressure there is. So literally, the pressure, atmospheric pressure, was defined as the height in millimeters of mercury that can be supported by the air pressure. And again, mercury is used because you have to have a very heavy liquid in order for this to happen. You technically could use water, but your tube has to be extremely, extremely tall. And that's the idea. And this is named after Evangelista Torricelli, Italian chemist of yesteryear. And that's really where millimeters of mercury come from. Usually torr is used just short, and we're going to use this a lot. So we can do a little conversion practice. Just like we did with temperature, we can do with pressure. It says convert 18.9 psi to torr and to bar. So in this case, you don't have to use an equation. You simply use the conversion factors. Now this is because all pressure units are absolute. There are no negative pressure units, whereas with temperature there was. So here we just do it the standard way, 18.9 psi. All right, we want to first get it to torr. So we'll put psi down here, we'll put torr up here, and then the relationship between those two, if you take a look previously, 14.7 psi is 760 torr. So really all you're doing is you're multiplying by 760, so we'll do 18.9 times 760 divided by 14.7. Try this, and you should get yourself 977 torricellis. Now if you want to convert this to bar, we actually have to first go to pascals and then to bar, because the relationship between bar is 10 to the 5th pascals. One bar is 10 to the 5th pascals, and then so we have to go from, and we have the relationship from torricelli to pascals. What I'm trying to say, if you take a look at the conversion factors, you don't have a conversion factor directly from torr to bar. You have to go through pascals. So we can do this. We can do 977, in this case torricelli. You can first convert it into pascals. So we'll go from torr to pascals. And then 760 torricelli is 300, is it 21.25? No, 101.325. That's right. 101.325. Make sure you have it memorized. 101.325 to be exact. Pascals. No, that's kilopascals. So 101,325. Ah, there it is. Unless you're European, then that will mess you up. Okay, and then 10 to the 5th pascals is defined as 1 bar. So these are the conversion factors. Hopefully I didn't confuse you too much, but let's do this calculation. Whip out your calculator. So we got that times 101,325 divided by 760, and then divided by 100,000. And that should give you 1.3 bars. 3 sig figs, so 1.30 bar. Alright? So that's how you would convert. Essentially, if you have the conversion factors, you got this. So go ahead and convert, take a minute to convert this, convert 93,200 pascals to millimeters of mercury. That should just be one step. Let's wrap up the chapter talking about what's called STP. And this is referred to as standard temperature and pressure. Now this is a set of conditions agreed upon, and many gases will be referred to as being at STP. That means you're at these conditions. It's a set of standard conditions that we can use for all gases. And it refers to 0 degrees Celsius and 1 atmosphere of pressure. So the temperature is 0 Celsius, the pressure 1 atmosphere. So an example of an application of this, anytime gases are reported, their densities, for example, are reported. If you think about the density of a gas as, 0.0032 grams per liter or something, they'll do it at STP, because as you'll see, the density of a gas changes as conditions change. So we have to specify the conditions, and those conditions are agreed upon to be 0 Celsius and 1 atmosphere. Another very interesting fact is that 1 mole of a gas, it turns out of any gas, of any ideal gas, so we should say 1 mole of an ideal gas that we've been talking about, actually takes up 22.4 liters, which is quite a bit. It's actually quite a big balloon if you were to blow up a balloon this big. So we can actually, as long as we are at STP, if the conditions change, then this volume actually changes. Now we'll talk about how to determine these numbers. We'll show you much more with these conditions as we keep studying gases. So this wraps up video 3 of Unit 6.